works. Do you hear me? Okay, so hi, I'm Čukić, and I'm a little bit of a peculiar person. So I'm here both from academia and kind of from the industry. So I'm from KD, which is one of the largest free software open source projects, and I work at Faculty of Mathematics. I usually talk about functional programming at C++ conferences. So this is a really strange occasion to me to talk about C++ at a functional programming conference. So my previous things, I authored the functional programming in C++ book. I usually talk at, as I said, C++ conferences. The key thing to note here is that I'm not a purist. So I really don't care that much about functional programming theory. If I need something to be done, then I'm going to do it even if it collides with mathematics. And I always start my talks with Phil Wadler's quote: make your code readable, pretend that the next person who looks at your code is a psychopath. The reason why I show this is that usually functional programming idioms in non-FP languages are a strange concept. And people often ask me, okay, but how do your colleagues react? My answer is always never cater to, let's say, beginner developers. Try to teach them something better. So the fact that something from FP is a little bit confusing to, I don't know, Java developers or whoever, that doesn't mean that you should write code as a normal Java developer. It means that you should teach a Java developer to write better code. So let's start with some parts of this talk. Will be a little bit more about C++ than you're probably accustomed to, because I wanted to show you that C++ is a really nice language even for FP. So one of the things that I always think about when I talk about functional thinking is that unlike normal imperative programming where you write the steps or algorithm, in FP it's usually you have input and then you perform some transformations. And the conveyor belt with some transformations is quite a nice way to depict that. The example that is a poster child of the difference from imperative and FP was in 1986, Knuth was asked to write a program which calculates the frequency of words. And his solution was 10 pages long in Pascal. It was a beautiful solution with a lot of documentation. He even created some novel data structures. And then they asked Doug McIlroy to give a critique of Knuth's work. And usually when you see a name like Knuth, critique cannot exist, right? But in this case, Doug just sent a snippet of Unix shell that was 6 lines long, which did exactly the same thing as Knuth's solution. Obviously, a little less efficient, but still 10 pages versus 6 lines. And this is FP. You have input and a series transformations. So shell is exactly what I'm trying to teach all the imperative programmers in the world. So in C++, we had algorithms, and we have a really powerful algorithm library which has transform, which is kind of like a map or fmap. We have copy, which can simulate filter. We can simulate folds, both left and rights, which accumulate. The problem with algorithms is that they operate on iterators, and iterators are usually, they come in pairs. For each sequence that you want to process, you have the begin and end iterator. And for example, calling map or filter looks like this. It's a little bit ugly. First, we have the input sequence as a pair of iterators. Instead of the transform giving the output as the output, the new sequence, you have to pass a single iterator where to store the data. And obviously, you have the transformation function. The cool thing about iterators is that they're really a high-level abstraction. They're not pointers. So instead of just having a beginning of a collection with pre-allocated data, you could say, okay, I want a special iterator, which will, instead of assuming that we already have enough space, any time that we want to store something into the back inserted iterator, it will just append a value to the epsilons. Apart from that, we don't even have to have normal collections. We can use iterators to traverse over input streams or output streams. So in this case, transform does what fmap does, but instead of storing values in some collection, it will print them out to the standard output. So iterators are on a good path to become a really great thing. But the problem is that, as I said, they come in pairs. So we can't return a pair of iterators from a function. It would look quite ugly. And we couldn't pass the result of one transformation, for example, from transform to filter or from filter to transform. And that's when something that is currently being proposed for standardization, but is available as a third-party library. Instead of having iterators, they have created an abstraction over iterators, which kind of contains two iterators at the same time. It contains a proper iterator, which can be a smart iterator like filtering or something like that. And it has the sentinel, which denotes the end of the range. So instead of having separate iterators, now we have a structure that kind of contains two iterators at once. And the lowest level for a range is that we can access an element and we can move to the next one. So the word frequency, the 10 pages in Pascal, would look something like this in C++. With a note that this code will not compile because the range library is not really that pretty, but it's almost compilable. So you have the data and a series of transformations that you want to apply to that data in order to get the frequency. And I'm not going to talk about ranges anymore. If somebody wants to ask anything, we'll have the time. The problem is, if you want to use ranges or something like that in FRP, it's a huge problem because accessing a value is something that is going to block your main thread or the program where you want to access the value from. So while ranges are really beautiful to define data flows, they cannot be used in FRP. So we should probably invent something of our own. Instead of normal iterators, we can create push iterators. And in general, it would look something like this. We have the input, we have the push iterator, and the output. Now, the key thing to note here is that it doesn't mean that for each value in the input, we have to produce exactly one value on the output. It can be arbitrary. So each push iterator can accept values and emit values. Just flip the normal iterator, which accesses a value and requests it, to something that accepts values and maybe emits something else. With push iterators, we can easily define reactive streams. So we could have a source, which is an iterator, which just emits values but doesn't accept. We have sinks, which accept values but never emit. And obviously, we have transformations, which are the general part of it. So as far as C++ is concerned, most of these push iterators are kind of like the continuation monad. So most of the iterators that need to send values can be modeled to inherit the continuator base class. Each continuation needs to store inside of itself, each continuator needs to store the continuation function. So it's going to be the generic argument for the continuator base class. And the only important thing that this class needs to do is to be able to emit values. Now, as far as the code is concerned, instead of having a normal function call syntax with m continuation of something, here a special function called stdinvoke is used because stdinvoke is a little bit more generalized. It supports both normal function call syntax, but it also can call member functions, so methods in Java or whatever. So if it's a normal function, it will call it like this. if it's a member function, it will consider the first argument to be the object on which we are calling the function on. So if we wanted to create our first push iterator, we can just inherit from the continuator base. And for each value that we are given that we need to emit, we can just call base : emit. This should be fairly trivial, right? And then we are going to get something like this. So we define values and pass some values that need to be emitted. As soon as the stream begins emitting, it will emit all the values one after another. So our task at hand today is to create a simple web service, which is not something that C++ is very famous for. It's going to get line-based input formatted JSON. It will be a bookmarking service, and the clients will send information about the bookmark in a JSON formatted fashion. The bookmark will look something like this. So it's a JSON which has the title and the URL. This is the JSON that DuckDuckGo search engine is using. If we wanted to create a source, we could collect all the clients and all the client messages and create just a service source which will emit those messages out. So as far as our system is concerned, even if the clients can be considered sources, our application doesn't see them. Our application just sees the central service class, which emits string messages. Okay? So for the purposes of our application, clients don't exist. The service invents the messages. I'm going to skip the C++ implementation. So in essence, this is using the Boost SIO, which is a synchronous IO library, which is a callback-based, quite powerful but really ugly library. So that's the reason why I'm going to skip the slides. The only important thing to note is that for any line that we are going to read, we are going to emit it. So everything is hidden from the rest of the service. After we have the source, so we have the values source, we also have the service source. Now we can create a sink. The thing that we have already seen, the continuation function, was only called by std_invoke, which means that a sink can be any sort of function at all. We don't even need to create a special type to denote the sink. Any function that we pass, it will be considered to be a proper sink. So creating a sink is trivial. We don't have to do anything. After we have the source and the sink, we want to create some kind of transformations. So if we wanted to create a map or fmap, we need to have a iterator that both accepts the values and sends them. For each value that we accept, we apply a transformation function to it and then emit the transformed value. Okay? What does it look like? Since in C++, functions are not only functions. Objects that have the call operator, the operator with parentheses, can also be invoked like their ordinary functions. So in order to create a transform push iterator, we can just define the call operator on it. And whenever that call operator is invoked, we are going to emit the result of calling mTransformation with a value. So again, fairly trivial. Filtering will do essentially the same thing. It will just use the value of invoking the predicate to know whether the value on which the predicate was invoked should be sent further on or not. So far, so good. So we have some simple things from which we can build more complex data flows. Now, we've seen that the ranges library uses the pipe operator like shell to connect different transformations. And so far, we just created nodes which emit values or process values, but we still don't have the language that supports the pipe operator. So we will need to invent a DSL, which will add pipes to the thing that we just created. So we want to support the same syntax as the ranges library. We have a source, then we pipe it through a series of transformations and get a data flow. In C++, if you want to create a DSL, embedded DSL, it's usually done through something that is called expression template. I guess in Haskell it's not that different. Instead of returning values, you're just returning the nodes of the abstract string syntax tree. And whenever you have a pipe or some other operator, again, you're just building the abstract syntax tree. When you want to create the exact pipe, then you evaluate the tree and connect all the nodes in it, or evaluate the tree. One of the things that we want to support is complete and full associativity of the pipe operator. So that somebody, if we have a pipeline, somebody wants to factor out a few lines into a special variable. So we want to use both the pipe, both as the monadic bind and as the Kleiseri operation. So it's not only for composition of monadic transformations or for applying a monadic transformation to a monadic value, but we want to use the same operator for both, because it's much more readable as far as I'm concerned. And we have two special cases. If on the right-hand side of the pipe operator is a sink, then we cannot connect anything else to it because it doesn't emit values. So we have 4 different cases when, depending on the types of the arguments on the left-hand side and the right-hand side of the pipe. The problem is that we don't have any class hierarchies here. So we didn't create any dynamic polymorphic huge structure so that we can deduce what is on the left-hand side of the pipe operator, what is on the right. These, both sinks, transformations, and everything else can be a completely different type, completely unrelated to one another. So if you tried to do it like this, if you want to be able to define a pipe operator for all the different possible types, we would need to use the templates. The problem is that in this case, this will swallow all the types in C++. So if we create a template function, which is called operator bar, and we say that both left and right arguments are template, this will work both for integers, floats, and everything else that we don't want it to work on. If you want to limit the scope on which types a template function can work on, there is a nice trick that existed a long time in C++ 98. We can embellish the types that we create with some metadata. In this case, we are creating a nested type, and we are saying that the values class, its category is source node tag, because it only emits values. Transformation, transform, filter, and everything else will have a special tag that is called transformation node tag. Okay? And then we can use something that is called detection idiom. In C++ 20, we're going to have concepts which are, let's say, a core language implementation of the detection idiom. And we can check at compile time which, for example, we want to say to check for a huge pipeline, to check whether every of the past things is a node. How can we check that? During compilation time, so if const expr, we are going to check, do we have a defined node category for this node? If it says no, then this is not a node, obvious. The second check is, OK, if you check for the node category and it returns us a void, it's not a valid node category, right? So we're just going to return false. Otherwise, the node category is defined and it has a valid value. So we are going to return true. The important thing about this function is that this generates no runtime code. Everything here is done by the GCC or Clang. During compilation, everything here is evaluated. So there are no jumps at runtime. Okay? And then we can use this in order to restrict our operator, pipe operator. We can say, OK, we're going to create a generic function which accepts a left and right as types. But we're going to require that the left argument is a node and that the right argument is also a node. Otherwise, this will be a compilation error. Or this function will not even be, the compiler will not even try to call this operator pipe on something that we have written. Further on, we can create just like we have created this node, we can create checks for whether something is a source, whether something is a sink, and everything else. So for the implementation of the pipe operator, we can, again, during compilation time for any of the left and right arguments, we can check if the left one isn't a source and the right one isn't a sink. Then we are going to create a Kleisler composition. Okay? If the left one is a source but the right one isn't a sink, then we are just creating a transformation of a source, which is again a source, just the transformed one. The same goes for the sink. And in the end, if the left one is a source and the right one is a sink, that means that we have the whole pipeline already defined. So we can finally perform all the connections between them and evaluate the AST. And now we can create a new source by transforming the old one. We can create a new transformation just by composing already existing transformations. And we can create a new sink by, let's say, pre-transforming values that go into the final sink. And then we can compose them in a single pipeline and evaluate everything. The cool thing about this way of programming is that reactive streams are usually difficult to implement because of the inversion of control. Here we can just define a huge pipeline and everything is transparently done. If something is asynchronous, it will be evaluated asynchronously and passed on. If it's not asynchronous, it will be synchronous, obviously, and the values will just go through the pipeline. The idea of the push iterators and reactive streams is abstract enough so that we can even create more advanced things. This pipeline that we have written, nobody said that all of the nodes have to live in the same process. We can just split the pipeline and say, OK, the first part of the pipeline is in the first process, the second in the second and third, and the processes will automatically just pass the values on. As an example, a really stupid program. So we have a single pipeline which calls ping on localhost and processes the results that the ping returns. It does some filtering, it does some, I don't know, transformations and everything else. And then we can just define, we want the processes to be split here, to be split here, and to be split here. So from a single source, we get 3 different executables compiled. The first executable calls the ping. The second executable accepts the values the first one sent, and so on and so on. And in the end, from the third executable, it sends back the data through the front end, through the first one. So we can define really nice way to, so we can create distributed programs in a really nice way from one single source to compile as many as we want distributed nodes. I have an example for this if you want to see it later on in action. So when we have created the pipeline, we can create our bookmarking service. So values, as we said, the source that emits values. we want to our service to listen to 3 ports, 42, 42, and 43, and 44. For each of those values, we are transforming. We are going to get, for each of the values, a new service. So it will be a source, a stream of streams of strings. Then we can join, just a normal monadic join. We are going to get a normal stream of strings. And then we can process those strings. OK? Now, when parsing JSON, one of the most popular libraries for C++ is the Lohmann's JSON. The problem with it is that it loves to throw exceptions. So instead of having error codes or maybe monad or, I don't know, partiality monad or something else, it just throws exceptions. In the pipeline scenario, we cannot allow any functions to throw exceptions because it will kill the whole process. Instead, we can do something that, let's skip because I don't really have that much time left. We can do something that I've seen that it's really popular in Scala. We can wrap anything that throws a function into something that returns an expected value, or in Haskell it would be either error or value. And if everything is OK, it's going to return a normal value. If exception occurred, we are going to return the unexpected, or the error state. So now we have one monad, which is the reactive stream. And by using this, we're going to have a nested monad, which is the expected or the either monad. One approach to handling this is, OK, whenever we have this nesting thing, we're going to filter out all the invalid values. And then we're going to call get. So we are just processing this in an ugly imperative way. Even if it's written like a pipeline, it still looks like this, which is bad, right? Instead, we know that the either or maybe are monads. So instead of using the is valid and get, we can just bind it, monadic bind it to a transformation. So if we have an expected value and we want to process it, we can just bind until we get to the final result. And when we have the error handling, it would look something like this. So far, we have error handling, we have reactive streams, but we have no way to reply to the client. The clients only send us strings, and we don't even know that the clients exist. We can add another monad into the mix, which would be based on a product. So monad called with_client, which contains a value, and it contains the ID of the client that sent the value. Obviously, it's going to have a reply member function for us to easily reply to the client. Now, we can reply because the last thing that is going to get what? An with client of expected of a value. And we can check. If the expected value is OK, then we are going to return everything is fine. If it's not OK, we are going to return that the request is not understood. OK? So we have a couple of, let's say, nested monads. The problem is that now all the filter functions that we already used are not going to work, because they worked on strings, not on with client of strings, or not with expected of with client of strings. The easiest way, if you don't want to do anything, we can just lift, transform, and filter the pipeline thingies to silently work with client. So we have created a with client monad, and then we just lift all the transformations in our pipeline to work with them. And this is quite trivial to do, and it will require absolutely no changes to the source code of the main program, the pipeline itself. It just predefines the transform and filter functions. The problem is that this way, we have to predefine them. So whenever we want to add another monad into our mix, we will have to predefine all the things that we used in the pipeline. The pipeline itself will not change, but everything that we are using in the pipeline will have to. Instead of that, we can go out of the pure and mathematical world. We can say, well, if somebody wants to call a transform on a nested monad, we can first try, OK, if it's a stream of with client of expected, let's try whether a function that is given to the transform can process the with client. If it can, then do it as a normal transform does. If it cannot, then ignore, OK, let's call it on the nested one. And again, if it cannot be called on expected because it wants to get std string, then try this one. So instead of just working on one type of having a transformation that can work on a single type only, we can check at compile time which of these can be evaluated. And instead of the invoke that we used earlier, we can create something that can be, for example, called multi-level invoke or lifted invoke or something else, which will try. Can this function be called on this type of value? If it cannot, well, if it can, then just call it. If it cannot, then use the fmap to call it on the nested monadic value. And then again, this can be stacked. So it can call recursively as many nested fmaps as it wants to. In that solution, we can create 3 different transformations. All of the transformations work on completely different types. But the transform will deduce exactly on which level of the monad stack it needs to work. Now, this way, if the original program was implemented like this, we could add as many different monad nestings as we want without having a single problem to change a single character in the original code, which is really cool. And I think I'm out of time, maybe for the questions. So I tried to do this as quickly as possible. And obviously, you can ask anything. I can go back to any slide that you want.
This is a very practical question. What do error messages look like that are generated by your compile time checks?
OK. As usual, in C++, whenever a question of what do the error messages look like, they look terrible. The good thing is that by using these things, blah, 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 blah. So by using, let's say, this simulation of concepts, we can do static asserts during compilation. And instead of having the huge template metaprogramming error, it will just assert on that message, and I can write the exact string that I want to be printed out. So if somebody wants to, for example, evaluate an incomplete pipeline, the pipeline that doesn't have both the source and the sink, it can just check, OK, is my type correct? No. Message, I'm missing a sink. So while usually in C++, template meta programs are awful to read the compilation errors, by using the concepts, it becomes much more simple.
I saw that in your case you just returned from after detecting an exception from as the expected?
In this case, in the sync. Did you remember the slide number?
No, you were quite fast.
Okay, this one.
Yeah, top. So in case, and this is okay. This is the sync, so that's the end node.
Mm-hmm.
What happens if, let's say, somewhere in the middle of the nodes something happens as an error? And do you have something to control the semantic of what's happening, or do you fix the behavior? Like, let's say, someone in the middle, an error comes from expected, but you already applied a few filters before, and I expect because this is C++, you did the mutation already, right?
Nah.
Yeah. Or just assume no.
I wouldn't say that we have made any mutations here, but that's another talk. As far as error handling is concerned, if you use the mtry, you're going to get the expected, which either has a value or an error message. And then you have complete control over how you're going to handle it. Now, in this case, this is a sync, so calling return is completely fine. Otherwise, you just pass on the error to the next transformation.
And in case, let's say, you already did the mutation, then you have to option, let's say, either you go reverse the mutation or...
There are no mutations in functional programming, not even in C++.
Okay, so just assume that the expression...
So in this case, if you want to build pipelines, each of the pipeline nodes needs to be completely isolated, just like in actors in Akka or in Erlang. So the idea here is not to abuse this and implement all the mutations in your program. The idea of the pipeline is to allow you to write normal function programming code, which would not do any evil stuff and yeah.
So what would the compile times look with this kind of pattern? What times can we expect? Because I've heard the compile times with type-level hackery can be quite long.
My answer to that is...
I haven't done C++ myself for a long time, so I don't really know.
So compared to C, yes, it will be awful. But compared to other libraries from C++, including the Boost, the synchronous I/O, it will be the same. So I did some benchmarking compared to normal just C code. It was, let's say, I don't really remember, but 10 times slower. But compared to normal C++, which already uses the SIO, it's just a minor influence.
Hey, so it looks all really nice. What I see missing is the typing and the constraint on the sync. So what you are doing here is a side effecting for getting back a reply, and this is not checked at all, and can be done eventually in any step of the transformation that you have shown as soon as you have this with client handler.
Okay. So syncs, since they don't emit values or anything else, the only thing that a sync can do is to change state. Otherwise, they will be just black holes that accept data and do nothing, right? So a sync is something that is allowed to change state. Just imagine like in the gloss library for Haskell or in the Elm. That's the final thing that gets the values. What exactly needs to be changed? Well, you can't have a constraint in C++ to disallow changing something. But it's something that you just need to, when you create a function, okay, create a pure function, and that's it. As for constraining the types, instead of writing auto in the lambda head here, you can just specify the exact type.
But this is the income, not the outcome.
For emitting types, again, you can create a transformation which does nothing but only does static assert on type. So just imagine a pipe and saying, OK, ensure type and which type you want.
okay, this should be done by the user, so it could not be inferred.
That can be written in 5 lines.
Okay.
I'm not going to do it live now.
That's fine, thanks.
We have time for one last question. Thank you.
I'm curious, how does the memory model work? Who's responsible for like deallocating? Because if you have a filter, you can probably deallocate the objects way earlier in the pipeline than if they go all the way to the sink. Or do you copy every time between the steps?
Okay, so the double ampersand in C++, it means that you're stealing the object from whoever sends it to you. So the memory model in this case is whoever created a value, that's where the value is created. And for example, in the, let's say, filter or transform, if it accepts a string, it stole the string from the original guy. If it doesn't emit it further on, it's immediately destroyed. There is no need for garbage collection and anything else. There are no superfluous copies or anything else. Just one item exists from its birth until it's ignored by the transformation.